Okay, let's talk about our solution notebook. So we can open it by following the same way. Click the GitHub and type BAOSENZ and hit enter. So you can click section 1 solution notebook in here. And then it's loading this notebook from our GitHub, and you click the copy to drive, and this also saves to your Google Drive. So in here, the solution for our assignment is in here. Here is your first blank, and then here is your second blank. See if you are right or not. And let's explain more about this solution Colab notebook. So first, you will load image dataset, and the image dataset is loaded, and we will use them to train our custom model, and all of the images are collected in our lab. So it's kind of different from the example closed classification, since there you will load images from using the keras function, but in here we will download the dataset from our GitHub. So you click it, and those code will clone the amoeba detection into our Colab notebook. So after it finish, actually you will see some files in here. So you click the files button in your left side, and you will see there is a new file or folder generated in here. So you will see it contains all of our dataset, section, all kind of the things. Okay, and then you click this code. What does it mean? It's copy the dataset from a GitHub folder to content. So if you refresh, you will see dataset amoeba classification. So actually this is the dataset inside this section 1. Okay, so we can use this dataset for further process to prepare it. So in this step, we will prepare data, including data augmentation, splitting training data, validation and test dataset, and a normalized dataset. Okay, and the first is the data augmentation. So what does the data augmentation mean? So it can obtain more data for training and validation. When the training dataset is small, we can do data augmentation to existing data and add those data to training dataset. For image data specifically, data augmentation could consider things like flipping the image horizontally or vertically, rotating the image, zooming in or out, cropping or varying the color, and so on. So this is called the data augmentation. And the process, the methods when we do the data augmentation is in here. We do the rotation, width shift, or height shift, and so on to get our data. Okay, more images, and we can click, and it will start to run. So this file is just for the train amoeba dataset, and the same thing with the previous block is just for train no amoeba dataset, and we also click it. This is for test dataset and test no amoeba dataset. So we run it, we will got more data. It's like more images. Okay, after you finish the data augmentation process, you can go to the folders to check your dataset. Like we want to check the training dataset, and you could click training and see amoeba, and you click it. You will see that there is a lot of dataset in here. So you find the images with the AUG in the as a prefix. Actually, this is the data we add after we finish the data augmentation. And you click it, you will see that this image, it's our data augmentation image. It's like there is shift in here in this image. Okay, and then you can split and normalize the data set. So by running this code, actually you create a X-string full array, and then you assign all of the images in our data set into the corresponding array. And then you will find out we have about 1077 training images. And then you do the test data preparation. After that, you will have 198 test images. So we will use these test images to test our model performance. You can click this code to visualize the training data. So you will see that for the dataset, there is many operations for the images and also some original images in here. You normalize the dataset, you normalize the images, that array, right? So the purpose of normalizing the dataset is to get a better model performance. And then you split the X-train and Y-train dataset randomly by using these functions. Since we will run our experiment multiple times, so to make sure each time have a different training data, so we will use these functions. And then we start to build and train the model. Okay. So for this process, since we need our experiments is repeatable and get stable performance, we will run for multiple times. In here, we choose number 6. So it means it will run our experiments 5 times. Okay, and then each time you will rebuild your CNN model, but the model is the same. And then you compile the model the same way and start to train the model. And then you save it in your files. Right? And you click to start, you will see the first experiments, you got 15 epoch. And the second experiment, you got 15 experiments, and so on. In total, you will have 5 different repeat, and thus you will get 5 different trained models. So you will evaluate the model. Since you get 5 different models, right? So after you running this code, it helps us to calculate the performance of each model. So let's see the first trained model, you get accuracy of this number. Second trained model, this is the accuracy, and this is the 5 trained model. And you average this trained model, you get the mean test accuracy is in here. Okay, this accuracy is not bad. And then if you want to run the inference, we will need to find out the best model among all of these 5 trained models. So this block of code is to help us find the best model. So after we run it, we will find out the best model among all of them, and then we use it to draw the plot, accuracy versus epoch. You just click it, you will get the plot like this. And then you use the best model among all of the 5, you run the inference. So this block is the same with the code in our example. So you choose the image you want to run inference. In here, we choose the number 1. So for the number 1, we can show the image, and it looks like this, right? As a human, we know that it contains amoeba. So how does the model tell us? So we run this block of code. It tells us if the amoeba exists or not. Here is the final output. Of course, you can also change the inference image number to 2 or 3, but the range should be in here because we have the total test data set of 198. Okay,